Hello, everyone. Thank you for your interest. My name is Alan. I'm a PhD candidate at Texas A&M University. This work is in collaboration with Shanghai Jiaotong University and Carnegie Mellon University. In this work, we introduce a new mixed integer conic program formulation for a traveling salesman problem variant with moving targets and multiple agents. Let me first introduce the problem through some practical applications. Consider the first example where a drone or multiple drones surveil a set of moving vehicles. Consider the second example where an interceptor destroys a number of hostile UAVs or rockets. And consider the third example where a robotic arm picks up a number of objects moving on a conveyor system. So let me formally define the problem. So we have one depot and a set of agents that must start and end its tour at the depot. The agents must visit a set of targets moving along piecewise linear trajectories. The agents and the depot are given in dark blue in the video, and the targets are given in cyan. The targets must be visited within their time windows. The time windows are given in magenta. So the moving target TSP is a generalization of the traveling salesman problem, the TSP. Hence, it is NP hard. And in this work, we assume the targets follow some predefined piecewise linear trajectories. And all the targets must be visited by one of the agents. And we present a new MICP, or mixed integer conic program, for the multi-agent moving target TSP. This is a brief literature review. The problem was first introduced in 1998. The authors introduced some exact and approximation algorithms, but for some very restricted cases where there are strict assumptions on the target trajectories. For example, all the targets move on the same line, or targets move on lines passing through the depot, or cases where majority of the targets are static. And then a year after, uh, approximation algorithms were proposed, but with similar cases where targets move in the same direction with the same speed. But then recently in 2022, a new exact MICP was introduced for the problem, and here the targets can move along some arbitrary straight lines. We'll be using this work as a baseline to compare against our work. So, given an instance of the multi-agent moving target TSP, the first step is to construct a problem graph. So in the instance here, we have three targets and three agents. First step is in constructing the graph is to define the nodes. And in the graph, the nodes correspond to the solid lines here, which are the time windows during which the targets can be visited. The nodes corresponding to each target are then clustered, as you can see here. C1 is the cluster of all the time window nodes for target 1, and C2 is the cluster of all nodes for target 2, and so on. The depot is also defined as nodes in the graph. There are two nodes for the depot, one for departure of the agents from the depot, and one corresponds to the arrival back to the depot. And now edges are constructed between nodes of different clusters. Once you have the problem graph, then the MICP can be defined on this graph. And by solving the MICP, we get a feasible solution to the problem. In this example, only two agents visit targets. The third agent just waits at the depot. So first, I will I will explain the baseline MICP that we previously saw in the literature review. And the reason I'm doing this is so that is because our MICP builds upon this. So the baseline MICP is similar to the Miller-Tucker-Zemlin or MTZ formulation for the traveling salesman problem. It relies on something called big M constraints. So first, let me introduce the decision variables. YEK is the choice of agent K traversing an arc E in the graph, and L is the distance traveled by that agent if it were to traverse the arc. TIK is the time at which an agent K visits some node I, and then L, X, Y, and L bar. These are auxiliary variables that are used to define the distance variable L. So this is the program. So the objective is to minimize the total distance traversed by all the agents. And the first few constraints are the flow constraints, which require that the agents start and end their tours at the depot, and that exactly one node from each target cluster is visited by some agent. We had time feasibility constraints, which require that the targets are visited within their time windows. And then we have this time feasibility requirement, which states that if an agent were to traverse an arc, then the distance traveled by the agent for that arc should not exceed the maximum distance that the agent can traverse as it moves from some target I at some time tj to some target I at time ti to some target j tj. However, if the agent were to not traverse that arc, then we need this constraint to be relaxed. The big T here is essentially a big M. This is a big M constraint, and the constraint linearizes a non-convex constraint such that it's enforced if YEK equals to 1 and relaxed if Y equal to 0. And similarly, we have another big M constraint here. The last three constraints to ensure that if an agent traverses an arc, then the cost of that arc is the Euclidean norm. But if it does not traverse the arc, then the cost should be 0. The big R here is the big M for this constraint here. So our idea is to first consider the MICP that was just presented, the one that uses big M method, and then reformulate this as a non-convex program by using product of binary and continuous variables instead of the big M approach. And once we have the non-convex program, then we reformulate this non-convex program as a new MICP by doing two things. The first thing is we replace agent-specific edge variables defined for each agent. We replace that with a shared set of edge variables common to all the agents. And we also convexify the product of variables differently, not using big M, but a better way. So this is an example of using one set of edge variables. So to allow the sharing of edge variables or edge flows amongst agents, we introduce a new integer variable alpha, which can take values from 1 to m, where m denotes the number of agents. And what we do essentially is we relax the flow out of the depot and into the depot to be equal to alpha. And then we effectively remove all these separate set of edge variables for each agent and replace it with one set of edge variables for all the agents, as you can see here. And now the next part is the convexification procedure. The idea is to take the big M constraint here and represent it as a non-convex constraint. Its product of variables here. The t variable is multiplied with the binary variable y instead of the big M term here. And once you have the non-convex form, then we convexify the product of variables here by introducing new variables that belong to higher dimensional cones. And so let me explain further. We use new variable zet to represent this product, tj with y, and z prime to represent this product, ti with y. Sorry, actually it's the other way around. So ZET represent the product TI with Y, and Z prime represents the product TJ with Y. And then we require that these new variables, which represents these products, they lie within the set that Ti and Tj belongs to, multiplied by the binary variable y. And by doing this, we require that when y equals to 1, then z takes the value of just Ti or Tj. And when y equals to 0, then the entire set shrinks to 0. And we use the same convexification procedure to convexify the constraints defining R costs. And one thing to note is that since the convexification removes the variable, the node variables Ti, to ensure continuity, we add a new set of flow constraints, which says that the time at which a node is visited is equal to the time at which the agent departs from that node. So this is the reformulated MICP, the final version. We only have a single sum, not double sum, because we only have one set of edge variables shared amongst all the agents. And this is the new flow constraints with the new single integer variable alpha. And these are the time feasibility constraints after convexification. And these are the constraints defining the norm after convexification. So now these are some numerical results. Here we vary the number of agents to be 2 for A, then 3 for B, and 4 for C, and 5 for D. And we average the results from 20 instances for each number of targets. So each 5, 10, 15, 20 targets, and each of this corresponds to an average of 20 instances. We look at two metrics, percentage gap and runtime. Percentage gap is the difference between the best upper bound and lower bound divided by the best upper bound found by the solver. When gap equals to 0, that means we found the optimum to the problem. And a runtime is the time taken to solve the instances in seconds. And as you can see here, we have a huge improvement in both the percentage gap and runtime. In fact, we have greater than 90% improvement in optimality gap in this case here, and up to 2 orders of magnitude reduction in runtime if you look at this case here. And similarly, we look at the single agent case, and now we vary the time window duration to be 20 for A, 40 for B, and 60 for C. And like before, we look at the percentage gap and runtime. And the improvements are not as high as having multiple agents, but still we have up to 40% tighter optimality gap and up to 1,000-second faster runtime. And this is a visualization. This is a single agent instance. On the left side, we have our approach, and on the right side, we have the baseline. And we find that the optimality gap is around half of the baseline. Both the approaches hit the time limit. And a thing to notice here is that the lower bound is a lot tighter for our approach, which means it has a better convex relaxation. And this is a 5 agent, 20 target instance. And similarly, again, we have a lot better performance for this instance, for this multi-agent instance. And by that, I mean we hit the 0% optimality gap. That is, we find the optimum for this instance in 500 seconds, as opposed to the baseline, which hits the time limit of half an hour, and the lower bound is still at 0, and the gap is at 100%. So we see a significant improvement in the lower bounds, especially for our approach for this multi-agent instance. And thank you for watching. That's the end of the presentation.